Welcome, everyone. For today's prep, we're going to see how to find the intervals of increase decrease for a function computationally using its first derivative. So, we've seen how to do this. In the previous lesson, what we looked at is, given the graph of a function, how do we just kind of look at the graph and figure out the intervals of increase decrease? So those intervals, those sections of the x-axis. Now we're going to see how to do this using the first derivative. And in order to do this, we just need a couple things. So we have something called the increase-decrease test. And what this says is that when we're looking at an interval from a to b, and our function we know is differentiable there. So again, this interval, you want to think of this as kind of like a section of the x-axis. What we have is that if our derivative is greater than 0, then our function f is increasing. And if our derivative is negative, it's less than 0, then our function is decreasing. So what we have is, again, we want to think of the derivative as giving us the slope of our curve. So if we have our slope is positive, what this is telling us then is that our function is increasing. And if our slope is negative, so if the slope of our curve is negative, that means it's pointing down. So our function is going to be decreasing. So I've written this as kind of a double inequality, or a double implication here. And that's not technically totally correct, but this is kind of the way you want to think of it. So if our derivative is positive, then our function is increasing. And if our function is increasing, then most likely our derivative is going to be positive. It is possible that the derivative could be 0 and our function is still increasing. So technically this isn't quite correct, this double implication, but it's close enough where this is kind of the way you want to think about it. Same thing for decreasing. All right, so what we're seeing here is that we're interested in where the derivative is positive and where it's negative. So we want to know, when is our derivative positive and when is it negative? And the only places where it can actually change signs are where the derivative is actually kind of right in the middle, it's equal to 0, or our derivative is undefined. So it kind of just jumps across the x-axis. So essentially we're trying to figure out, where is our derivative positive, where is it negative? And the only way it can change signs is if it crosses the horizontal axis or if it jumps across the horizontal axis. And these two special places, where our derivative is equal to 0 and where our derivative is undefined, well, we've looked at these a little bit with our graphical section for looking at the intervals of increase, decrease just by looking at the graph. And we called these special places critical numbers. So we say x equals c is a critical number of the function f if either the derivative is equal to 0 or the derivative is undefined. Now, we're going to be interested in these points regardless of whether x equals c is actually in the domain of the function. So just to kind of specify and keep track of things, when we do our sign chart, and we're going to be doing a sign chart, we're going to use a filled in point to denote a critical number. So that means it satisfies one of these conditions and it's actually in the domain of our function. And we do want to give a name to the other things. So it's, like I said, it's going to be important just to keep track of these regardless if our point is in the domain or not of our function. So we'll call those non-critical points or non-critical numbers. And when we do our sign chart, we're going to use an open dot. So these are not in domain. So they still satisfy one of these two properties, but they're not. The number is x equals c is not necessarily in the domain of our function. So these critical numbers, essentially, these two conditions here, this is where f prime can have a sign change. So these are the only these are the only places where f prime can have a sign change. So we're really going to be looking to know when is f prime positive and when it's negative. And so to kind of give us the, when it starts being positive and when it ends being positive, to kind of separate things, we're going to look for these places where the sign change might happen. And so this gives us our strategy. So let's formalize our strategy here. So if we're trying to find the intervals of increase, decrease for a function, we're going to want to calculate the derivative. Then we're going to want to figure out where the derivative is equal to 0 and where the derivative is undefined. So we want to figure out both places, or all the places that satisfy those conditions. Then we're going to do a sign chart for f prime. So we write out our sign chart. And then we're going to go through and actually fill our sign chart in. So we're going to determine the sign of f prime for each interval section of the x-axis. All right, so let's try an example. Let's look at example 1. See how this strategy works. So we're going to find the intervals of increase and the intervals of decrease for some function f. And we're not given the function f in this example, but we are given its first derivative. So f prime of x is x times x minus 1 squared times x plus 3 raised to the power negative 3. So if we're keeping track, in this example, derivative's already done for us, so we don't even have to calculate that. Normally, for later examples, we're going to have to calculate it, factor it, simplify it, all that. But for right now, our derivative is given to us, and it's really nicely factored. So now we want to look, when is our derivative 0 and when is our derivative undefined? And so when we look at this, we want to get our derivative factored, which this one is already factored. And if we have negative exponents, let's write it as a fraction. Usually a good idea, just to kind of see what's going on. So if we rewrite this just a little bit, our first derivative becomes x times x minus 1 squared divided by x plus 3 cubed. All right, so we have our derivative all nice and factored, looking nice. So that's the first step. And that was basically done for us. Now the second step is we want to look for those places. So we want to figure out when is our derivative equal to 0 and when is our derivative when is our derivative undefined. So the nice thing about writing this as a fraction, it actually helps us a little bit. So the only way a fraction can be equal to 0, so since our derivative is a fraction, the only way that fraction can be equal to 0 is if the numerator is equal to 0. And the only way a fraction can be, well, the most common way that a fraction can be undefined is if the denominator is 0. So this is what we're looking at. We want to figure out when is our numerator 0 and when is our denominator 0. So we look at just the numerator, and we're going to set just the numerator equal to 0, and we're going to solve this for x. And it's nice and factored, so we can quickly solve this. This x factor gives us x equal to 0. And then the x minus 1 squared factor, well, really the only way that factor can be 0 is if the x minus 1 is equal to 0. So this gives us the solution x equal to 1. So we get two places where the derivative is equal to 0. Then we want to set our denominator equal to 0. So we're going to take the x plus 3 cubed, set that equal to 0. And again, we want to solve this for x. So we want to solve that for x. And essentially what we have here is 3 copies of x plus 3. So we can just take the inside part here and set that equal to 0, and we get x equal to negative 3. All right, so we have kind of three important values here, two of which are where the derivative is 0, and then one of which is where the derivative is undefined. All right, so now we're going to do our sign chart. So for our sign chart, we're going to start by drawing the x-axis. So here's our x-axis, and it goes to minus infinity in one direction, off to plus infinity in the other direction, and we're going to want to plot these x values. So let's do, maybe put -3 here. We'll put 0 here, 1 here, and that's all we have, those three values. And what these three values do is they slice up our x-axis into little pieces. So we got this one piece that goes from minus infinity to 3, or -3 rather. Then we've got this other piece going from -3 to 0. Then we've got the piece going from 0 to 1. And then we've got this piece going from 1 to infinity. And ultimately, the goal here is to figure out whether f is increasing or decreasing on these intervals. And to do that, we're going to first figure out the sign for f prime. So when we do this, we want to go through, and there's various ways we can do this. I think the easiest way is to just list all of the factors of f prime. So we're going to kind of write out a table here. So we have three factors. We have the x, we have the x minus 1 squared, and then we have that x plus 3 cubed. And what we're going to do is we're going to figure out the sign for each of these factors, and putting it together will tell us whether f prime is positive or negative. And then finally, that'll tell us if our original function f is increasing or decreasing. So now we're going to go through and we're going to fill in this sign chart. Again, kind of think of this as a table of values. So we're going to fill this in now. And what we're going to do is we're just going to determine for each of these factors, is it positive or negative on each of these four intervals. So let's start with x, the x factor. So when we're looking at this interval, all of these values are between -infinity and -3. So x is going to be negative. And then when we're between -3 and 0, x is still going to be negative. But then once we get onto the other side of 0, in between 0 and 1, those are all positive values. So x is going to switch to positive over there. And then from 1 to infinity, x is going to be positive again. Now let's go to the next factor, x minus 1 squared. And the nice thing about when we have something squared is that no matter what's going on inside the parentheses, if this whole thing was positive in there or if that whole thing was negative in there, when we square it, we end up with positive. So for an even power like this, we can just go right across and say it's always going to be positive. All right, now what about x plus 3 cubed? Is this going to be positive or negative on these intervals? And if you're ever unsure, you can always use a test number. So this can be helpful. So if we're going to do a test number, let's look at this first interval. So we want to pick a test number that's somewhere less than -3. So it's got to be in this interval. So let's try -4. -4 fits that description. And when we plug it in, we get -4 plus 3 cubed, which is -1 cubed, and that's just -1. So when we're doing the test number, we don't really care about that number, we just care about the sign of that number. So in this case, it's negative. Now what about What about the next interval? -3 to 0. Let's see what we get there. Again, if we're not sure, we can use a test number. So we just want to pick something in between -3 and 0. And let's try -1. Plug it into that factor. We get -1 plus 3 cubed, which is +2 cubed, which is +8. So that's just positive. And then if we pick something in this next interval from 0 to 1, so let's say 1/2, if I were to plug that in, I'd have 1/2 plus 3 cubed. Everything's positive. So positive again. And if I were to go to this last interval, pick a number, let's say +2. +2 plus 3 is +5. +5 cubed is also positive. So what we've done is we've broken our derivative. We've broken this derivative down, and we're looking at each of the individual factors. And so now we can actually kind of put these factors together. And we're multiplying and dividing. So when we have, so let's look at this first interval from -infinity to -3. The x term was negative, the squared term was positive, and then that cube term was negative. So essentially in this case, we have a negative number times a positive number divided by another negative. So essentially we have a double negative here, which cancels out to just positive. So that means f prime would be positive on that interval. So now we go through our basically our columns here, and if there's an even number of negatives, it's just double negatives, they cancel out, and we're left with positive. If there's an odd number of negatives, well then it ends up being negative. And so all positive means f prime is positive, all positive means f prime is positive. And now we can make our conclusion. This is what we're really after here. So when f prime is positive, that means our original function is increasing. And when f prime is negative, that means the original function is decreasing. So now we can actually write out what the intervals of increase decreasing are. So f is increasing on the interval from -infinity to -3, the interval from 0 to 1, and the interval from 1 to infinity. And f is decreasing on that interval from -3 to 0. Now, we can't really put union signs in here because it's not necessarily increasing all the way across all these intervals. So if we plug a value into this first interval, doesn't necessarily mean that a value from the second interval plugged into this function is going to be bigger. So we kind of have to keep these intervals separate. So I'm just listing them out. So the function does move upward on this entire interval, and it does move upward on this entire interval, and it does move upward on this entire interval, but it's not necessarily true that it goes up uniformly across all of those intervals. We'll probably look at that in a graph in class. All right. So let's stop there for today, and we'll see you in class. Bye-bye.